Alright, so we're going to have a look at equations of tangents. This is a really great application of derivatives. So we're going to start by kind of looking at some definitions and then getting into some examples. So just a reminder of what a tangent actually is. That's a line that touches a function at one point, exactly one point. Remember, that's kind of our instantaneous rate of change. And this is so where the gradient of that line is the same as the gradient of the function at that point. So essentially where the gradient is the derivative. And we can find the equation to these tangents very similar to how we would find the equation of any line. We're just going to use the derivative to get the gradient. So let's start with a little bit of a warm-up, taking ourselves back to maybe grade 9, grade 10. So I'm giving you a point, the point 1, 3, and a gradient of 2. I would like to find the equation of the line that goes through that point with a gradient of 2. Well, just a reminder of kind of our default equation, y equals mx plus c. Remember, m is our gradient, whereas c is our y-intercept. So the first thing we're going to do is to substitute in the gradient for m, meaning replace the m with a 2, just like this. So I get y equals 2x plus c. Okay. Then as it says here, the next thing we're going to do, well, I want to solve for c. I don't like that I have x, y's, and c's. I would just like to solve for c. So I'm going to substitute in the point for x, y. So that means my 3 is going in for my y, and my 1 is going in for my x. So putting the 3 in for the y, 1 in for the x. Now I just need to solve for c. So multiply them together, subtract the 2 over to get that c is equal to 1. Again, I had that my equation was y equals 2x plus c. C is 1, so I can clearly state that the equation of the line is y equals 2x plus 1. And we're essentially going to go through that procedure, but instead of being told really explicitly what the gradient is, we're going to have to use calculus, use the derivative to find that gradient, which is again what the tangent is all about. The gradient at a particular point is the derivative, which is the tangent. Okay, so here's the process that we're going to go through to find the equation of a tangent. So modeling the example we just did, essentially we're going to look for the tangent of a function f of x at a point x equals a. So it might say find the tangent at the point 1, 7, or it might say find the tangent at when x is equal to 1. Okay, so we might just be given the x coordinate. So the first thing we're going to do is use the derivative to determine the gradient of the function at their particular point. We may need to do a little manipulation. We might talk about if it's perpendicular, it's called a normal. So we may need to do some little changes to it, but that's the basic idea. Take the derivative, plug in the point, and that gives me the gradient at that particular point. The next thing we're going to do, I need an x-coordinate and a y-coordinate. So I'm going to take my x-coordinate, plug it in to get my y-coordinate. So I'll have my gradient, I'll have a point, then I just do what I did in that last example. Substitute in the gradient and the point to determine the equation of the line. So let's do kind of the fundamental example. It's going to look something like this. So what is the equation of the tangent to the curve y equals x squared plus 6x minus 7 when x is equal to negative 1? So again, we could go ahead, try and graph it, maybe use technology to help us, but this is kind of the true tried, tested method. So if I want the equation of a tangent, that's the equation of a line, meaning I need y equals mx plus c. So I'm going to start by finding the gradient, particularly the gradient at x is equal to negative 1. Well, the first thing I need to get the gradient is my derivative. So remember, to take the derivative, we bring the 2 down, so I get 2x, and we decrease the powers by 1, so I'm just left with 6 constants. The derivative is 0. So my derivative is 2x plus 6, but I don't care about what the derivative is in general. I just care at the point negative 1. So if I now plug in negative 1 for x, okay, so the derivative at negative 1, well, that's negative 2 plus 6, or 4. Okay, so the derivative is 4 at the point negative 1, meaning the gradient of the tangent at -1 is 4. So I've got my gradient, check, happy, happy. Now I just need a point. Well, the point -1 something. I basically need to figure out the y, and then I'm good to go. So finding the coordinates of the point at x equals -1. Well, that's as simple as going back always to my original function, okay, because it's the point needs to be on the original function because that's where the tangent is. So I'm going to plug -1 in for my x. So I get -1 squared plus 6 times -1 minus 7. Simplifying, I get -12. So I've got the point -1, -12 on my curve. Recall from the previous slide, my gradient was 4. The point -1, -12 is on the line. I've got everything I need to get an equation of a tangent. So here we go. I start with y equals mx plus c. That's my standard equation. I fill in my gradient. It was 4. That's what we did first. We found the derivative, plugged in -1. Gradient was 4, so now I can plug that in there. Now I can go ahead and plug in my point, -1 and -12, remembering that the x coordinate was first, the y coordinate was second. And now I just need to simplify and solve for c. Moving the plus, adding 4 over, I get that c is -8. So my gradient was 4, and my y-intercept is -8, so I can state my final conclusion. The equation of the line is y equals 4x minus 8. Really, I could have been more specific than that. It's not just the line, it's the equation of the tangent at x equals -1. Okay, and you can confirm this by graphing. So if you were to plot the curve y equals x squared plus 6x minus 7, so plot that on your CAS, and then plot the line y equals 4x minus 8, you'll notice this line will run exactly tangent to this curve when x is equal to -1. You might need to zoom out a bit because the point is down at 1, -12. So that's our standard kind of example for finding the tangent. We can go into a little bit more kind of problem-solving style by maybe having to work backwards, not being given the x values. We can also kind of do a little bit more finding equations of normals, which is where we take the gradient and take the negative reciprocal, because a normal is what is perpendicular to a tangent. So that's the fundamentals. Stop here, maybe do a couple examples, and then have a look at the next video, which is a little bit more problem solving.